Good morning, champs. Today, we're diving into an essential tool for tackling problems in three-dimensional space, spherical coordinates. In many real-world scenarios, such as describing planetary motion, modeling electromagnetic fields, or analyzing sound waves, Cartesian coordinates aren't always the most efficient choice. Spherical coordinates offer an alternative way to describe points in space using angles and a radius, simplifying problems with radial symmetry. In this lesson, we'll break down the system step by step, see how it relates to Cartesian coordinates, and explore practical examples where spherical coordinates really shine. Let's get started. Now that we understand spherical coordinates, let's move on to setting up a triple integral in Cartesian coordinates and transforming it into spherical coordinates. Imagine we're working with a triple integral over a domain, D, where we have a function f of x, y, and z. In Cartesian coordinates, this integral is written as the triple integral of f of x, y, z with respect to x, y, and z over the domain D. To transform this integral into spherical coordinates, we introduce generic variables, u, v, and w, as placeholders. These will represent the transformed coordinates before we define their relationships to spherical coordinates. The integral then becomes the triple integral of f of x of u, v, w, y of u, v, w, and z of u, v, w multiplied by the determinant of the Jacobian matrix with respect to u, v, and w. Here, the determinant of the Jacobian matrix accounts for the change in the volume element when switching between coordinate systems. This ensures the transformation preserves the geometry of the space. Next, let's map our generic variables to their counterparts in spherical coordinates. We define u as the radius, r, v as the azimuthal angle, phi, w as the polar angle, theta. Using these variables, Cartesian coordinates x, y, and z are expressed in terms of r, phi, and theta as follows. X equals r times sine of theta times cosine of phi. Y equals r times sine of theta times sine of phi. Z equals r times cosine of theta. This mapping transforms each point in the Cartesian domain into the spherical domain. Essentially, we're reinterpreting the space using r, phi, and theta as the new variables to describe any point in three-dimensional space. This change allows us to take advantage of spherical symmetry, making computations more efficient. To construct the Jacobian matrix, we calculate the partial derivatives of x, y, and z with respect to r, phi, and theta. Using these derivatives, we form the Jacobian matrix. The determinant of the Jacobian matrix simplifies to negative r squared times sine of theta. When we take the absolute value of the determinant to transform the volume element, it becomes r squared times sine of theta. This positive factor ensures the volume element is properly scaled in spherical coordinates. To define the boundaries for the transformed domain, we consider the following limits. Radius, r, from 0 to r, where r is the radius of the sphere. Azimuthal angle, phi, from 0 to 2 pi, covering the entire circumference of the sphere. Polar angle, theta, from 0 to pi, covering the full vertical span of the sphere, from the North Pole to the South Pole. These boundaries define the transformed domain, representing the region of the sphere in spherical coordinates. Finally, let's calculate the volume of a sphere using what we've learned, starting with the triple integral over the domain. After transforming the integral to spherical coordinates, it becomes the triple integral of r squared times sine of theta with respect to r, phi, and theta. The integral of r squared times sine of theta with the boundaries. R from 0 to r, phi from 0 to 2p, theta from 0 to pi. The solution gives the final answer. The volume of the sphere is 4/3 pi r cubed.